All right. So good morning, everyone. I think we'll get started. Just a couple reminders items here. So the next three homework assignments due dates on the screen here, and then the exam three will be on the Friday at the end of this month. Okay. So the next homework due date will be on the Thursday, the 15th. Make sure you finish them by Thursday midnight. Okay. Um, we are going to still looking into the chapter 9 today. So we'll get started with what we learned last time, yesterday. So last time we talked about different types of collisions. So two big categories for collisions. So elastic collision and inelastic collision, okay? And then whenever you see collision happens, if not specified, you can assume that the external forces can be ignored in this scenario. So you can apply conservation of momentum there, okay? And then if you see, if it says the collision is an elastic one, then you can also apply conservation of kinetic energy, okay? All right, and then for the inelastic collision, there's a special case when you have completely inelastic collision. When that happens, two objects stick together after the collision. Okay, so when that happens, you have the loss. You will have the maximum loss in kinetic energy. All right, so for an elastic collision, then you can write out two equations, conservation of momentum before and after, and then conservation of kinetic energy before and after. Okay, so from two equations, and then if you are looking for two unknowns, then these two equations should be sufficient to solve for the two unknowns. Okay. For inelastic collision, on the other hand, then you can only write out on one equation. Okay, for the conservation of momentum there. Okay. And then last time we also checked collision in multiple dimensions. We took a look on the example of two-dimensional collision. So then the initial momentum in x direction should be equal to the final momentum in x direction. So that means you combine the momentums from the objects involved in the system, okay? And then also the y component initial should be equal to final. Again, you are talking about the combination of the y components for all the object in the system. Okay. All right. Today we are going to started expand with expanding the concept of the collision and then integrate that with what we learned earlier. So conservation of energy. Okay. So we will start with this example over here. So I think we are going to check on this example together, and then you guys will have the chance to solve a problem on this particular integrated concept by yourself and on the next slide. Okay, so let's take a look on this one together here. Let me stop sharing. Let me read the problems first, and then I will stop sharing so you can see the bigger screen on my side. So it says a ramp of mass. So the big ramp that has a mass of capital M is at rest, okay, on a horizontal surface, and then there's a small cart of small mass M is placed at the top of the ramp and released. So what are the velocities of the ramp and then the car relative to the ground at the instant the car leaves the ramp, assuming the ramp is frictionless, okay? So if you see wheels and then rolling down here, so then the friction for a wheel, if it says it's not slipping down or skidding down, then that friction should be should be the static friction. Okay, so in that case, then because it's static friction, so then you will not consider like the work done by a static friction, because static friction, that means it's not having relative motion. Okay, so also on this case, because you have wheel on the ramp over here, so then there will be static friction between the floor and then the wheels. Okay, so then there will be no effect on the kinetic energy or mechanical energy there. Okay, so if you examine the scenario over here, when this guy ramps off, so we are going to just ignore the frictions on the ramp and then also from the ground here, right? So then there's no external forces on the system of the ramp and then the small cart. So then you can apply conservation of the momentum, okay? So which that when you apply it when the collision happens. So this is might not necessarily be a collision, but you can treat it in the way you treat a collision, okay? Now also look at this carts rolling down here. There's no friction, and then normal force is perpendicular to its motion. So then work done on this cart is only by the gravitational force, okay? So then you can apply conservation of mechanical energy here as well, okay? So in this case, then you'll set up two conditions. You'll set up, let me stop sharing for right now. And then you guys on your end, you probably want to click on the speaker view, okay? All right, I'm gonna just switch my camera. All right, so two conditions, conservation of momentum. So that means initial momentum should be equal to final momentum. So initially, P initial should be equal to P final, okay? And then KE initial should equal to KE final. So these are the two conditions you will apply here. Initial momentum over here. Now we'll just focus on the horizontal direction, okay? Because you can, when you examine the scenario over here, initially the two objects are at rest, right? And but at the final status, the two object will have just horizontal components, right? So that's the one we are focusing. So initial condition Pi should be equal to 0 because the two are at rest, okay? Now for final condition, you can see the small cart in the on the slides. If you have the slide pull up on your end, you can see from the slide there, the small car is going to the left, right? So if you take to the right to be positive, so then you'll have minus small m times v of the cart, okay? So let me call it v1, okay? Or you can do v sub cart, and then plus the capital M, the mass of the ramp times the velocity of the mass in the horizontal direction. So I'm going to call that v2, okay? So this negative sign because the car is going towards the left, okay? Now for the ramp, it's going to the right, so it's positive. So this is conservation of momentum. Now for conservation of mechanical energy or kinetic energy initially, we should do, sorry, we should do that's just mechanical energy. So UI plus KI should be equal to KF plus UF, okay? So you can take, so for the vertical position change, it's only for the cart, right? So you can take the cart, the low position as your potential energy ground level. So that means U final for the car is going to be 0, okay? U initial for the car is going to be mgh. Now, for the ramp itself, because the position doesn't change for the ramp, so it doesn't really matter if you put out whatever like capital mg times the position of it, y2, then initial should be also mg y2, okay? So this will cancel out anyway when you set up conservation of mechanical energy, okay? So you can ignore the potential energy for the cart, for the ramp, sorry. For the ramp, we will just cancel out, okay? So then initial potential energy should be mgh, okay, plus kinetic energy. The two are at rest, so it should be 0, add up to b. And then final potential energy should be 0, okay, because the cart is at the low position, plus the kinetic energy 1/2 m v1 square plus 1/2 capital M v2 square. Okay, so you have these two equations. You can solve for v1 and v2. Okay, so to do that, you will just write, so v1 and v2 are the unknowns, okay? v1 and v2 are the unknowns. And then the rest, you can treat them as the knowns given because they are given in the problem, okay? So then you write one unknown in terms of the other one. So in this case, you can write v2 in terms of v1. So then v2 in terms of v1 should be mv1, small mv1 divided by capital M, okay? And then take this expression into the second equation over here. So take it in over here. Okay. So then the second equation becomes mgh on the right hand side equals to 1/2 small m v1 square plus 1/2 capital M. Now this guy mv1 over capital M and then square. Okay. So you'll expand the square, so you'll give you 1/2 small m v1 square, and then on this side is again small m gh plus 1/2 capital M. Now small m square v1 square divided by capital M square. Okay. So then on the second term over here, you can see capital M over here will cancel out the square there. So leave one capital M at the bottom here. Okay. You will also see the capital or small m across the terms here. So then you can cancel out m, but cancel out just the square on this term here, leaving one m here. Okay. So then it's gh on one end, on one side, and then this is 1/2 v1 square plus now 1/2. You will have small m over capital M. Okay, small m over capital M times v1 square. Okay. You can multiply both sides by 2, like get rid of 1/2 and 1/2. Okay, so then on the right hand side is going to be 1 plus small m over capital M times v1 square. Okay, equals to 2gh. All right. So then if you rewrite this term, this would be capital M at the bottom here, capital M plus small m at the top. Okay, so v1 square 2gh. Then you divide both sides by this term to give you v1 square. Okay, so then 2gh divided by this will give you capital M plus small m at the bottom, but capital M at the top. Okay, equals to v1 square. Okay, so then for v1 here, you'll take square root of it, right? And then take square root of this guy. Okay, so you will figure that v1 then is equal to square root of 2gh times capital M over capital M plus small m. Okay, now keep in mind initially when we say this guy, the velocity for the cart should be towards the left. Okay, so then you want to put a minus sign on the v1 here, indicating this is towards the left. Okay, so this is minus. Okay, for v1. All right, so once you have v1 here, then v2 can be solved. v2 is equal to m v1 divided by capital M. Okay, so equals to m over capital M, and then v1 you will just take the magnitude. Okay, 2gh capital M over capital M plus small m. This time it should be positive. Okay, because for the ramp is going towards the right. Okay, so pay attention to the signs you got. All right. Any questions you guys might have? All right. So let's go back to the PowerPoint slide here. So if you guys are clear with this one, you can go ahead and then try this example by yourself. Okay, so this one again, it should be a combination of conservation of momentum and then conservation of mechanical energy. Okay, so you'll but in this case, you'll divide the motion into two parts. One is upon collision, on the collision, and then one is after the collision. Okay, so you apply conservation of momentum before and after the collision, and then you can also apply conservation of mechanical energy right after the collision, then to where the final position where when the bubble reaches the maximum height. Okay, so I will have you guys have a try, and then we can take a look at the solution in a few seconds, in a few minutes together. Okay. All right, I think a couple of you guys have submitted your answers already. We can take a look here together, okay? So does this collision happen when the bullet strike the bob here? So then this is a collision here, okay? And then after the collision, the two should stay together, okay? And then this system of the bullet and the bob here will have an initial velocity, okay? You can call it the V, or VI if you like. So then they will swing up. So it says swing up to a maximum angle of 60 degree or the maximum height. When the maximum height is reached, the angle is 60 degree. Okay. So then when it reaches the maximum height, so let's take a um, analysis here. So when it's at the maximum height, right? So then its final velocity is going to be 0, right? Because then that if that's the maximum, so you'll go up, reaches the maximum, and then comes back down. Okay, so this is what the motion of pendulum bob will go back and forth, back and forth. But when it reaches the maximum height, the final velocity will be 0. Okay, so the initial velocity, it's not given here, but we are looking for this guy, right? So when collision happens, you can write momentum initial equal to momentum final. Okay, so the initial momentum of the bullet plus this bob should be mv0, small mv0 plus capital M, the mass for the bob here times its initial velocity should be 0, right? So this is the initial momentum. That should equal to the final momentum of the system. So final, the two stick together. So you can add their mass up, and then the velocity, you can say that's the V here. Okay, so this is the V after the collision. Okay. So this is conservation of momentum. Now, after the collision, when it swings from this low point to the high point, okay, you can see that when this happens, there's this tension in the string, which is always perpendicular to V, to the motion at any given moment. So then work done by tension is 0, so you can apply conservation of mechanical energy, okay? So then the second one, you are applying conservation of mechanical energy. That means initial kinetic energy plus initial potential energy should be equal to the final kinetic energy plus the potential energy. Okay. Now you can take the low point here to be your potential energy 0. So that means Ui is equal to 0. So Ki is equal to, should be equal to 1/2 the mass, combined mass, V squared, right? For the final potential energy, this should be mg y. Y would be then this guy here, this y here, right? This height. This is your reference point, so this is the y. This y should be equal to the whole length minus the length of this part, okay? If this is 60, this is L, okay? So then this is L cosine 60. So your y then would be equal to L minus L cosine 60 degree, okay? And if you are very good at trigonometry, you might realize that cosine 60 is equal to 1/2. Okay, so that's equal to 1/2. So then y is equal to 1/2 of L or small l. Okay. All right. So this is then mg small or 1/2 small l, and then kf is equal to 0 because final velocity is 0. Okay, when it reaches the high point. So then the second equation you can write over here is Ki, which is 1/2 small m plus capital M V square plus Ui, which is 0, okay? And then equals to Kf, which is 0, and then Uf is mg 1/2 L, okay? L is the 2.3 meters, okay? So then you have these two equations. So you have two unknowns here. So you have V0 and Vs unknowns, okay? So you should be able to solve for the two unknowns by using these two equations, okay? It looks like you can solve V by just looking at the second equation, okay? And then once you have V there, you can take V into the first equation, you can solve for your initial V0. That's what you're looking for, all right? So let's start from the second equation here. You're looking for V. So then you multiply both sides by 2 to get rid of this, or actually this 1/2 here, this 1/2 here will cancel out. Okay, so then um, V square is equal to MGL divided by M plus capital M. Okay, so then V is equal to square root, if you take square root of the both side equation, all right, so then V is equal to square root of MGL over M plus capital M. Okay, now you can take this into the second equation here, then you can figure out your V0. So from the second equation, you can see that MV0 equals to M plus capital M times V, which is square root of MGL over M plus small m. Okay, all right, so then V0 equals to, you can take this one into the square root. Okay, so it becomes, oh, let's do this first. Let's do small m plus capital M divided by M first. Divide both sides by M, and then square root of MGL. Okay, so then this will give you, basically, you can see this part over here. This is outside the square root, and then this part is inside the square root. This is inverse of this guy, right? So then when you take this into the square root, it will become small m plus capital M divided by small m times GL. Okay, so times G times L, and then the whole thing square root. All right. So let me see. Looks like there's something went wrong here. Oh yeah, right. I got it. So on here, for the potential energy over here, this should be capital M plus small m, okay? Because they are together. So capital M plus small m there. Sorry for the math there. So then, yeah, 1/2 cancel out. This guy will cancel out that guy, okay? So then V squared is equal to just G times L. Sorry about that. So this guy goes away, square root of GL, okay? So then square root of GL here, okay? So it actually will give you, so this is not right, okay? I apologize for that. So this is then equal to, so V0 is equal to then small m plus capital M over small m times square root of GL, okay? All right. Then you can plug in your numbers. So small m, so it's 15.0 grams. So you want to convert it into kilogram, okay? So 15.0 times 10 to the minus 3 kilograms plus 1.80 kilogram, okay? And then divided by the small m, 15.0 times 10 to the minus 3 kilogram, okay? And then multiply square root of g, 9.8 meters per second square times 2.3 meters, okay? So all this together will give you 574 meters per second as the initial velocity of the bullet, okay? All right. Any questions you guys might have? Yeah, and then the responses I got from you guys are all about, I got several responses. They are all about 574. Okay, so you guys got that right. I think it has to do like when you do your algebra step by step, has to do some like rounding up error, but that should be fine. Okay. All right. So if you are clear, then we can move on. The next section of this chapter talks about center of mass. Okay. So so for center of mass, so usually you might have an object, okay, that's made of different parts. Okay, so for example, in the figure here, the toy doll has like the two arms, two legs, and the body, and then the head. Okay, so several different parts, they have different center of mass, or sometimes it's referred as center of gravity. Okay, so if you see center of mass or center of gravity, they are referring to the same um, um, meaning. Okay, so the meaning are the same. So if somebody call it center of mass, some people may call it center of gravity. So for the center of gravity of an object, that is where you can treat the system, where the mass and the weight of the system can be acted as if they are located at a single point. That single point is called the center of mass. Okay, so for the toy doll here. So the arm might have center mass over here, and then this arm have center mass there, and then for other parts of the body. But you can treat the center of the mass for the toy, the whole, as somewhere here, okay? Because they, if you put a pivot point through this point, then you will be able to balance the toy in there, okay? And when you are having a system that is in balance, okay, so that is if so if you have if you call a system to be in a stable equilibrium, okay, so that means if the system, the object is, or the system is displaced from the equilibrium to the slightly, then there will be a net force or torque to pull it back towards that equilibrium point. Okay, so that force and then the or the torque is called, or the, yeah, so for the force, it's called the restoration force. Okay. Um, so let's take a look here in detail about the quantitative analysis of the system. If you say, if you have two masses here, the balance being here is light, and then the streams are light as well. So then you have a system made of two parts, M1 and M2. Okay. So then where would be the center of mass of the system? Okay. So if you take a origin of your system, like the X direction over here, so if you are just focusing on the X direction, the horizontal direction, then where would be the center of mass in the horizontal direction? Okay, so take this where the pivot point it is. Okay, so the pivot point is where you can actually support the system, and then it will be in equilibrium. So in this case, then the pivot point is the origin you can choose. Okay, now it doesn't matter where you choose to be your origin. Actually, it doesn't really matter. Okay, but then at the end, the pivot point should be your center of mass. Okay, so for the center of mass for two objects, then you'll be doing the mass of times the x coordinate system of the object one, m1 times x1, plus mass 2 times the x coordinate of the two object 2, and then divide by the combined mass. Okay, or capital, just use capital M to be the combination of m1 plus m2. All right, if you have more than two objects, then you'll be adding up the rest up. So basically, the mass of each object times the coordinate of each object, and then divided by all the masses adding up together. Okay, that will give you center of mass for the X, and then you can do the same for Y. They will give you the center of mass for the Y coordinate. Okay. For an irregular shape of object, so you can actually determine the center of mass by just hanging it at 2 points. Okay, because when you hang the center of hang an object, okay, with a string over here, then the center of mass should be along this line. Okay. If not, if say the center of mass over here, then you can see gravity is acting on this point. Okay. So then it will pull the whole object towards this line, center line, this line going through the center of mass. Okay. And then on the other hand as well. So it has to be equilibrium through this line where it goes through the center of mass of the object. Now you can hand the object at another point, a point B here. So then again, um, the vertical line through point B should be going through the center of mass. So when these two lines intersect, that will give you the center of mass of this irregular shape. Okay. So if that's how you can determine if an object, the center of mass for the object, if the object is an irregular shape object. Okay. All right. So let's take a look on this example. It says 0.34 kilogram meter stick balances at its center. If a necklace is suspended from one end of the stick, the balance points move 9.5 meters towards the end. Okay, so basically it says the meter stick, originally the center of mass is at the center. Okay, so that's how it's balanced. And then it says if you suspend a necklace from one end, then the point, the center of mass of the whole system moved 9.5 centimeter towards the end. So find the mass of the necklace. I- Um, so on this one, I will have you guys again give it a try by using this center of mass equation, and then we can take a look at the solution together in a couple of minutes here. Okay. right, so I think we can take a look on this one together here, okay? So for a meter stick, okay, so the whole length should be 1 meter, right? Or 100 centimeter. And then when you do not have the necklace over here, it's pivot at the center over here, okay? So then this is the center, where's the 50 from each side, okay? 50 centimeter from each side. Now it says if you have a necklace on one end, now you might be drawing on this end, that's fine. Then the pivot point will be moved towards the end, okay? So I have it on the left end, so then the pivot point is going to be moved towards the left, okay? Now I'm going to set up my X coordinate system this way towards the right to be positive, and then at the middle here to be 0. So it doesn't matter, okay? So, but I figure on this one, it will work out. Just pick it at any point here. So now for the system, you will have the necklace plus the meter stick. Okay, so you have two objects in the system. So then your center of mass X position should be equal to M1 X1 plus M2 X2 divided by M1 plus M2. Okay. So if you set up the coordinate system like this, then the center of mass for the system should be 9.5 centimeters away from the origin in the negative direction. So minus 9.5 centimeter then is equal to M1. So let me take the mass of the necklace to be M1, okay? And then the mass for the meter stick should be M2. In this case, it tells you it's 0.34 kilogram. All right. So then I'll put M1, X1. So X1 will be the position of the necklace, which is 50 centimeters from the origin. So negative 50 centimeter, okay? Plus M2 multiplied by X2. X2 will be the position of the meter stick. So I choose this to be 0. So then that's 0, okay? So then M1 plus M2 down here. Okay, so this is M2, it's also 0.34 kilogram, okay, but this is 0. So then the second term on the top actually goes away, it's 0. 0.34 multiplied by 0 should be still 0, okay. You also will realize that this is positive, negative here, this is negative here, so the negative and negative will cancel out, becomes positive, okay. So then you'll be solving for your M1 here. So you can multiply both sides by this denominator over here. So 9.5. Now you will also realize centimeter and centimeter will cancel out. Okay, so you can leave out the units for right now. Times M1 plus 0.34 kilogram equals to 50 times M1. Okay. So then this is 9.5 M1 plus 9.5 multiplied by 0.34 kilogram equals to 50 M1, okay? So you can move this M1 to the other side of the equation. So 9.5 times 0.34 kilogram equals to 50 minus 9.5 times M1, okay? Then you will divide both sides by 50 minus 9.5 to get rid of this, okay? So let's multiply by that, divide by this, will be your M1. So this is 0.080 kilogram as your M1, okay? All right. Questions you guys might have?
Excuse me.
Yes.
I just want to clarify exactly. So it might just be my misunderstanding of the problem, but I'm not looking at the problem, but the necklace is suspended on one end. Okay, because
Right.
my confusion was with where the necklace was. The
Okay.
50 would come by that the 0 is the center of the meter stick, correct?
Yeah, right. So
Okay.
it has to do where you set up your origin, okay?
Okay.
Yeah. You can set
Thank
up
you.
on the origin to be where the necklace is. So then the X1 will be 0, okay? Then X2 will be 50, okay? Yeah.
Okay.
But yeah, the result should be the same. The mass you should get is the same of 0.080. Okay. All right. So yeah, so let's move on here. Um, so we have just talked about like one-dimensional in X direction. Okay. So now you can expand this into two-dimensional and then also three-dimensional. Okay. So if that's the case, then you'll represent the position as the position vector. Okay. So instead of X, you'll be writing like R with the arrow on top. So and then with the subscript or CM, that means the center mass position for the whole system. Okay. Then again, if there's multiple objects in the system, you'll do just M1 times R1 in vector form plus M2 times R2 in vector form. So basically summation of the mass times the position vector of each object, and then divide by the overall mass, capital M. Capital M will be summation of M1 plus M2 plus M3, etc. Okay. And that will give you position vector, the center mass of the for several objects in the system. Okay. And then the velocity vector will be time derivative of the position vector then. Okay. And then for the acceleration, you'll be doing double derivatives of your position vector. Okay. So that's basically the same we learned before. All right. So on the other hand, so that the previous slide deals with if you have multiple objects in the system. Okay. Now, on the other hand, sometimes you have an object that is having the mass distributions to the other body. Okay. So as one side of the body might be you might have more of the mass, and then the other side might be having less. Okay. It's not uniformly distributed. Okay. So throughout the location. Okay. Location wide. So then in that case, you have continuous distribution of the message throughout the object. So in that case, you will be doing the integration. Okay. So integration of the position vectors with dm, the small increment of mass, and then divided by the overall mass of the system. Okay. That will give you the center of mass for the object. Okay. And so this one, it says if you have a rod of length L where the mass density changes from one end to the other end quadratically, okay? So in another word, that is, if the rod is laid out along the x-axis with one end at the origin and the other end at x equal to the length L, the density then is given by this equation over here. Density rho as function of a position x is equal to a constant rho sub 0 plus rho 1 minus rho 0 times x divided by L to the square. Okay, so that gives you a quadratic formula here, where rho 0 and rho 1 are constant values. Okay, so then what would be the center of mass of this rod? I don't think we have time for this, but if you guys have get a chance, you can work on this one. We can start on this one tomorrow. Okay, so I'll stop here for today, and then see you guys in class tomorrow. Okay, all right, bye.